Today, we're extending our understanding of the transformer, an idea we first explored in case number TCM 183000. It revolutionized NLP, and it all started with this paper, Attention is All You Need.
Right, that's where we learned how self-attention replaced recurrence for efficient sequence processing. But this title feels even bolder than I remember. What was the core claim of this paper?
The paper started by noting that for tasks like machine translation, the dominant sequence transduction models are based on complex recurrent or convolutional neural networks. These were the state-of-the-art before transformers.
And the problem with those, if I recall, was that they processed information sequentially, making them slow to train on long sequences. The transformer promised a solution to that.
Exactly. They proposed a new simple network architecture, the transformer, based solely on attention mechanisms. This was the paradigm shift. Attention wasn't just an add-on, it was the foundation.
So they stripped away the old mainstays. What did that allow the transformer to do differently from previous architectures?
The key was dispensing with recurrence and convolutions entirely. This meant no more waiting for the previous step to complete, unlocking true parallel processing of sequences.
That's huge for efficiency. But beyond just speed, did this architectural change also improve performance?
Absolutely. The paper demonstrated that these models were not only more parallelizable and requiring significantly less time to train, but also superior in quality, setting new benchmarks for machine translation.
So it was faster and better. That's the ideal scenario for any new architecture. And machine translation was the initial proving ground.
They tested it on tasks like the English to German translation task, where it surpassed previous state-of-the-art models. This immediate success cemented its place in NLP.
It makes sense for language. Words are discrete tokens in a sequence. But what about other types of data, like images, for instance? That's not a sequence of words.
The paper hinted at this potential, stating the transformer generalizes well to other tasks by applying it successfully to English constituency parsing. This showed its flexibility beyond direct translation.
Okay, but parsing is still text. The core question for me is, how can a model designed for a sequence of words possibly interpret a two-dimensional image? Pixels aren't words.
That's an excellent question, Maya. It gets to the heart of how a seemingly specialized architecture became a universal tool. To understand that, we need to revisit the core intuition of self-attention itself.
Let's dig into that intuition then. What exactly is self-attention doing that makes it so adaptable?
This article, The Illustrated Transformer, helps us visualize the architecture. It explains how the transformer, a model that uses attention to boost the speed of neural-machine translation.
So speed is a huge part of its appeal, which we just discussed. What's the fundamental reason it's so fast?
The article emphasizes that the biggest benefit, however, comes from how the transformer lends itself to parallelization. This is the game changer compared to recurrent networks.
The ability to process all parts of the input simultaneously instead of one by one. This is key to scaling and making it practical for large datasets.
The transformer consists of an encoding component and a decoding component. The encoder processes the input sequence, and the decoder generates the output sequence, making it a powerful pair.
So the model takes an input sequence and codes it into a rich representation, and then the decoder uses that to generate an output. Where does self-attention fit in?
Within the encoder's inputs first flow through a self-attention layer. This layer allows the model to dynamically weigh the importance of different parts of the input. And here's how it does it.
So, before any traditional processing, each part of the input gets a chance to look at every other part. What does look at really mean here?
It means self-attention allows it to look at other positions in the input sequence for clues that help refine the understanding of the current word. Think of it like cross-referencing within a dense research paper. While it helps connect related ideas, unlike a human, the model isn't consciously remembering, but performing a mathematical comparison to blend information.
Like when I'm reading a complex sentence and I have to remember the subject from earlier to understand the verb later. It's building internal connections.
Precisely. The article gives the example, the animal didn't cross the street because it was too tired. Self-attention allows it to associate it with animal. This is crucial for disambiguation.
That's a classic NLP problem. So instead of a human explicitly programming rules for it and animal, the model learns these relationships dynamically.
Yes, it learns to bake the understanding of other relevant words into the one we're currently processing. This results in a much richer, context-aware representation for each word or token.
This baking sounds a bit like how an RNN's hidden state aggregates information over time. But you said transformers don't use recurrence. How is this different?
That's a good comparison, but here's where it differs. In a transformer, the word in each position flows through its own path in parallel, all at once. The connections are direct, not sequential.
So each word's representation is informed by all others simultaneously, not just the ones that came before it. This parallel computation is what gives it the speed advantage.
Exactly. Now, let's get into the actual mechanism. How does self-attention quantify these clues and associations to dynamically blend information? It uses a clever set of vector operations.
I'm ready for the technical details. How do we actually compute this baking of information from other words?
To start the self-attention calculation, for each input vector, which is typically a word embedding, we create 3 distinct vectors, a query, key, and value vector. This is done by multiplying the original input embedding by 3 different learned weight matrices, WQ, WK, WV, transforming it into these specialized representations.
3 vectors from 1? What are these 3 vectors, and what role do they play?
They are a query vector, a key vector, and a value vector. Think of it like a search engine. The query is what you're looking for, keys are like tags or indices, and values are the actual content you want to retrieve. This analogy is strong for how a query finds relevant keys to access values. However, unlike a search engine sequential lookup, here all queries compare to all keys simultaneously, and values are blended, not just retrieved.
So each word asks a query, and other words offer keys. If a key matches a query, that word's value content becomes relevant. Is that the analogy?
Yes, that's a precise way to think about it. The parallel to a search engine is quite direct in that sense. But remember, this isn't an explicit question and answer process. It's a measure of similarity between high-dimensional vectors that determines how much influence one token's content, value, has on another. The next step is to calculate a score for how relevant other words are. This is done by taking the dot product of the query vector with the key vector of each other word.
The dot product measures similarity, right? So a higher dot product means the query word is more interested in that keyword. This gives us raw relevance scores.
Correct. After scaling these raw scores by the square root of the key dimension, which in the original paper was 64, so we divide by its square root, 8, to ensure more stable gradients. We then pass the result through a softmax operation.
This normalizes them into probabilities.
Softmax ensures the scores are positive and sum to 1, like a distribution. So now we have weights, indicating how much to attend to each other word.
Yes, the softmax score determines how much each word will be expressed in the output representation of your current word. It's the learned interpolation weight we talked about.
So if the current word's query strongly matches another word's key, that other word's value will contribute a lot. But how do we combine these values?
First, we multiply each value vector by the softmax score. This effectively scales the content of each word by its attention weight, giving more emphasis to the relevant ones.
This is where the baking happens. We're selectively taking parts of other words' meanings based on their relevance.
Finally, we sum up the weighted value vectors. This weighted sum becomes the new, context-aware representation for our initial word, incorporating information from all other words, weighted by how much the model attends to them. It's a truly context-rich representation.
So the output vector for it isn't just its original embedding. It's a blend of it, animal, and other relevant words, weighted by how much the model attends to them. It's a truly context-rich representation.
Exactly. This parallel computation of attention is incredibly powerful, allowing transformers to handle long-range dependencies. However, this power comes with a trade-off. Can you think of any potential limitations for a mechanism that compares every token to every other token?
Well, if you have a very, very long sequence, like an entire book, wouldn't comparing every word to every other word become incredibly expensive? The number of comparisons would grow really fast, quadratically with the sequence length.
Precisely. That's one of the main limitations. The computational cost of self-attention scales quadratically with the sequence length. For sequences beyond a certain length, it can become prohibitively expensive, leading to innovations like sparse attention or local attention to manage this.
So the quadratic cost means you can't just throw any arbitrarily long sequence at it without hitting resource limits. It's not infinitely scalable in its raw form.
That's a key pitfall. While powerful, vanilla self-attention makes careful architecture choice to make the computation of multi-headed attention mostly constant, crucial to manage computational complexity and memory for very long sequences, or you'll quickly run into bottlenecks. This is why variations exist.